Hello Dr. Wu. My name is Aashik and today I'm going to present my project on a low-cost surveillance system using a Raspberry Pi. These are the topics that are going to be discussed in depth in this presentation. After this presentation, there will be a demo explaining the code and 2 trial runs uploaded to YouTube for Dr. Dapangbu to take a look at. Now, let's look at the motivation behind this project. Computer vision and machine learning algorithms today require a huge amount of data for producing accurate results. Hence, more computational resources are required, which have led to the use of large powerful servers and GPUs. However, when access to these expensive machines are limited, I would like to explore the possibility of using a small, low-cost machine to perform these computer vision tasks. Let's move on to the introduction. Surveillance can be performed by detecting motion in images. This can be done by a relatively simple algorithm called frame difference technique. It is essentially calculating a matrix which contains the absolute difference between the frame with foreground or frame with motion and the background image. This gives higher intensity pixels at the areas which differ from the background. Further, Gaussian blur and frame averaging techniques are incorporated into the algorithm to improve the results, and the user is alerted by a text asking him to check his Dropbox account, which will contain the motion detected images. This is called a smart alert system. Let us take a look at the steps of the proposed algorithm in detail. The first and foremost step is capturing the RGB image, which is later converted into a grayscale image. In order to remove or average out the noise, a Gaussian kernel function is used with a width and height of 21 pixels. Then, the pixel intensities above a certain threshold are converted to binary 1 and the rest are assigned binary 0. Dilation is then performed to close any holes that may be present within the foreground image. Let us now take a look at the images obtained with and without these techniques. In the first image, no Gaussian blur and dilation were used, hence we can see a lot of noise which is not desirable. The second image, however, gets rid of the noise by using Gaussian smoothing, and the holes found in the second image are closed by using dilation, as you can see in the third image. Let us take a look as to why frame averaging is required. In order to account for varying lighting conditions as the surveillance goes on for a long duration, it is necessary to ensure that the reference image is constantly updated. Hence, a background model is created, which is the average of all the frames up to the previous frame and the current frame. However, less weightage is given to the current frame when averaging using OpenCV's accumulate weighted function. Now, let us take a look as to how the frame detection is performed on the image. Using the contour area, we can determine the area of the foreground. Only areas above a certain threshold are considered while the rest are ignored. A bounding rectangle is then drawn on all areas above a certain threshold using the coordinates obtained. Now, let us take a look at the smart alert system used in the algorithm. Once there is a desired amount of motion detected, a text is sent to the user which contains the message "Motion detected, please check Dropbox," as seen in the screenshot in the presentation slide. Simultaneously, the motion detected frames are then uploaded to the user's Dropbox account. Let us now take a look at the results. The first image is the background image, while the second image is the current frame with motion, or the image where a person enters the frame. Let us now take a look at how the algorithm performs. The motion frame is first converted to a grayscale image and Gaussian smoothing is applied to it as seen in image number 4. Then image number 4 is frame differenced with the background model to obtain the frame difference image as seen in image number 5. Then it is passed through a threshold to obtain the logical image seen in image 6 and dilation is applied to it to obtain image 7. Then the contours of the foreground mask in image 7 are calculated, and if it is above a certain threshold, its coordinates are obtained and a bounding rectangle is drawn on the person, which can be seen in image number 8. Let us now take a look at the results obtained from this algorithm under varying conditions. Here False motion error occurs due to falsely detected frames, while failed motion error occurs due to missed motion frames. In this case, in indoor, well-lit condition, there is not much room for error, and hence the accuracy is almost 100%. Now, let us move on to outdoor conditions with good amount of lighting. Here, the overall accuracy dips slightly below 98% due to false motion error, which occurs due to a high amount of noise present outdoors. Now, let us take a look at the performance indoor under low light conditions. Here, you can see the performance is still good with a slight increase in failed motion error though. However, when we move outdoors under low light condition, the performance falls under 90%. This is attributed to the high noise and low illumination present in the captured frame. This slide gives the overall performance of the surveillance system. The accuracy calculated is about 95.29%, which effectively suggests that it is a good surveillance system. Now, let us look at an in-depth analysis as to why the surveillance system behaves differently in different environments. False motion, as we have seen already, is attributed to the noise in the image, while failed motion is usually predominant in low light due to frame difference image having lower pixel intensities than the threshold. Also, most of the error occur during transition between motion and non-motion frames, and thus these errors can be discarded, although they have been included in the results for fairness. Thus, we can conclude that with future models of Raspberry Pi having more powerful processors, we can further process higher resolution images and incorporate more complex computer vision algorithms. These are the references which were used in the projects. Let us now take a look at the code and the subsequent demonstration of the two trial runs. We first initialize the Pi camera library for 640 x 480 images, and we allowed the camera to warm up for a period of 5 seconds. Then we loop through the raw data captured by the camera. Line 46 converts the captured RGB image to grayscale image, while line 51 applies Gaussian smoothing to the grayscale image. If this is the first frame that is captured, then the average frame is assigned the value of variable G scale found in line 51, and the raw data stream is cleared for the next frame. This is taken care in the lines 54 to 59. Then accumulate weighted function is used to calculate the average for subsequent frames, where alpha is equal to 0.5 is the rate at which the current frame is forgotten. Frame difference image is calculated in line 66, while line 68 and line 70 involve converting it into a logical image and dilating it respectively. Lines 75 to 84 involve finding the contour areas above a certain threshold and then its coordinates. Lines 86 to 96 then take care of the Smart Alert text system. Here, the user credentials are removed with X's as seen for security purposes. As you can see, the Smart Alert system is triggered in line 87 when the number of motion count increases a threshold 3. Lines 99 to 101 draw the bounding rectangle and other necessary information onto the image. Line 106 is the one which uploads the motion detected images to the synchronized Dropbox folder, which is connected to the user's Dropbox account. Now, let us take a look at the live demo of this code present in the next two videos.